Okay, good morning, everyone. Welcome to now episode number 20. Wow, who knew we'd be getting to 20? I think this all started with the idea of trying to get 6 or 7 in there to try to get them all, but now we've got 20 and at the end of 2020, so that's kind of nice. Thanks again for joining. My name is Alex Bassini. I'm the Business Development Manager here at AWC. I'm also a water treatment specialist here with the company. Today we're going to be doing the principles of water chemistry. It is more of a review with everything that we've been doing. So thank you for your time. We might be going a little over 20 minutes, but I promise we'll try to keep it as short as possible. Somebody had mentioned that we wanted to kind of get back to the basics of water just because we were going in all of these separate directions. So year end, and this is going to be the last episode before we go into 2021. It'd be good to kind of go it all. So let's get started. So, and this is part of a 20. So far now we're at 20. We're going through them all. If you have any questions on them or you want to review some of the ones that you missed, please, I'll include a link to YouTube channel. You can go there and go over them. We've kind of ticked through all of these, and it's kind of nice to be able to wrap up the year with 20 of them already. So for those of you that are logging in for the very first time, AWC, who we are, we design and manufacture water and wastewater treatment plants worldwide. We've been around for 40 years, and we're based out of Vancouver, Canada, but we do a lot of work in North America, and of course now we're expanding into Latin America. And we've also done some projects in South Africa and Ireland. So how about that? That's quite the spread. So this is kind of our core competency. We do potable water, wastewater, and then we also go into some of these skid-mounted systems. Kind of reverse osmosis, pressure filters, and UF. We just finished working on, we're bidding on some desalination plant right now in Chile, so that's kind of exciting. So principles of water chemistry, we're kind of taking it back to the beginning here to see how this works. So before we go into the chemistry, which I know everybody's going to love, let's take a look at water sources because it's so important to identify where it's coming from first before we actually go into the water chemistry. Identifying where it's coming is a very important part of making sure that you can go in and see what are we looking for. Divide it into some groups there. So we've got our groundwater or surface water and wastewater. We won't be touching wastewater today, simply because that on its own is quite the review. I mean, we can go in there for over an hour. We're going to focus more on the chemistry around groundwater and surface water. Of course, we divide them into these two categories. We identify, well water is, by mere nature, we're looking at groundwater, and surface water, that includes, lakes, springs, shallow wells, of course, under surface water influence, and rainwater. Yes, I do add rainwater to surface water and now wastewater. There are some specific standards in the US where they like to see it in the wastewater side, but being a part of ARCSA, which is the American Rainwater Harvesting Association, I simply can't bring myself to put it under wastewater. It should be treated as surface water. You are still treating much like, organics and disinfection as well, and pH for that matter. So now that we've been able to identify where the water is coming from, we can take a look at some of the common contaminants. I did mention this was a review, guys, so bear with me. On the contaminant level, some of the typical contaminants that you would find in groundwater. You're looking at your hardness, carbon carbonates, iron, manganese, metals, hydrogen sulfide. Well, it's not a metal, it's a gas, but you do find it in deep wells. It's basically that pungent odor you get coming off of wells. Turbidity. Now, well water typically has lower levels of turbidity than, say, surface water, whether you're looking at lakes or rivers. But there are some wells that do have turbidity levels, whether it's silt or other turbidity that will show up. Now, less common, but we want to make sure we're looking at them just the same. You've got your arsenic and uranium, some of your heavy metals, and that also applies to radium and tannins. Now, again, tannins is not very common, but if we look at wells, Gary, you're working on a well right now that was just deemed GARP, which is underground water influence. You can potentially see tannins and organics if you're looking at shallow wells. And surface water. Again, surface water is pretty easy to identify. You basically strip out the metals that you'd be worrying about. Somebody asked me why you don't look at metals in surface water. It's not that you don't, but iron oxidizes and precipitates in nature. So when you're bringing it out of a restricted environment like a well, you bring it up to the surface, it's going to oxidize and precipitate on its own. So you don't typically test for it in surface water. Not that you shouldn't, you can always take a look at it. The same thing applies to uranium and arsenic just because it precipitates a lot slower. But these are the main ones we focus on. So you've got your organics, your turbidity, nitrates, and sulfates. In some areas where you have a lot of irrigation or farming or even agriculture, you are going to see nitrates and sulfates fluctuate in there. Organics and turbidity, something else that we came about, of course, was cyanobacteria, so blue-green algae. That's something that contaminant, but I don't know that you would really directly test for it in your standard lab report. That would kind of fall under a slightly different category. Uncommon, like I mentioned, were hardness, arsenic, and uranium. Not that surface water isn't hard. There is surface water that's hard, but it wouldn't be at the top of your list when you're looking at treatment. Uranium, interesting enough, is something that gets ignored a lot when we look at surface water. However, there is, often enough, there is certain levels of uranium in surface water. I did a project out in Adams Lake where they completely ignored the uranium just because it was below the threshold. Mind you, interesting fact, in Canada we have a different, shouldn't say tolerance, there's no real tolerance for uranium, but it is a different MAC guideline in Canada than in the US. They were testing at 19 parts per billion, and yes, the cutoff is 20, so they simply didn't highlight it. Now, it's not to say that treating, consuming water at 19 parts per billion of uranium is good for you, but it was something that would be considered to discuss with the community. Okay, I've got a little feedback there. If you don't mind muting your mic there on your end. Thank you. Okay, so now we go into the periodic table. That's what everybody signed up for. Okay,
Bye-bye. Bye-bye.
Okay, 1 second. We're going to make sure that we have everybody muted. Thank you. So that's what everybody showed up for, the chemistry. You got to love this, okay? Yeah, oddly enough, chemistry was not my favorite in high school, and here we are 20-odd years later. Okay, maybe closer to 25 years later. So we have divided this into specific categories because we are focusing on water. So we are going to have 3 different categories. So we're going to have our minerals. Somebody asked me why you don't oxidize minerals. Well, minerals don't oxidize because it is in fact a mineral, whereas we've got our metals. Iron and manganese, and this might be a little controversial, and I know I'm going to be corrected and get some slack here from this group, but they're not considered a heavy metal because there's no toxicity level to them. So it's still considered an oxidizing metal, not heavy metal. That label might be changing in Canada simply because manganese has now been changed from the aesthetic objective to the MAC objective, but that's a whole other subject. And then we go on to our heavy metals. Yes, there's a long list. Yes, you can treat for them. There are different ways of going after treating them. A lot of them co-precipitate. Technically, uranium is not on the heavy metal list, but I've thrown it in there just because we've treated for it and we've tested for it. And way back when, this was actually one of the ones that I focused on a lot, uranium and arsenic. So we've kind of divided them into categories. So we've got our minerals, we've got our metals, and we've got our heavy metals. Okay. So we can't talk about contaminants without making sure we discuss our limits. Okay. So in the US, we have the MCL, which was set by the US Environmental Protection Agency or the US EPA. In Canada, we have Health Canada, which set something called MAC, or maximum acceptable concentrations. You'll see that sometimes, whether you're in the US or in Canada, I'm bouncing around between MCL and MAC, but it is basically the same. They were both set at very similar levels. I'm not going to go through the list. Again, this is a review. In the US, you have very specific levels. In Canada, there's only 2, if I remember correctly, there's only 2 that are different right now. Mind you, there's 250 plus of them, so don't quote me on this. But the ones that are different are uranium. So it's 30 parts per billion in the US, while in Canada we have a set concentration of 20 parts per billion, and now manganese has just changed from aesthetic objective to from MAC now, excuse me, from the aesthetic objective it's now changed over to MAC, whereas in the US it's set as MCL. Mentioning aesthetic objective, here it is. So it's a parameter that does not have a toxicity level or has not been labeled as a toxicity level that applies to organics or TDS and iron. Yes, your water won't smell good, and a lot of times it won't look good either, but it's not going to kill you. Mind you, you don't want to drink water with tannins. You don't want to drink water with iron or manganese either. So that's the threshold of aesthetic objective to MAC. Throwing in some units of measure because I know that this is a pretty broad crowd. We have a lot of people from a lot of places here. Oh, hi, Jorge, how are you? So, so we want to make sure that we cover this all, and units of measure is something that gets lost in translation. It kind of is between North America, you go to Europe, you go to Latin America, you go to the Middle East, and they're always going to be throwing different numbers at you. It's important to understand where all of them fall. And I've highlighted GPM and GPD because this is one of my small pet peeves. And why not? Gallons per minute is a unit of flow. Gallons per day is a unit of volume. And the reason why it's important to identify the two is I can't have somebody come to me and say, I need 2,000 gallons per minute. If I don't know your daily volume, whether it's peak flows or average flows or seasonal flows for volume, that doesn't help me because I don't know if it's going to be rated at 3 hours a day or 24 hours a day. And of course, there's a stark difference. The same thing applies if somebody comes to me and says, I need 50 MGD. Yes, you see it's up there, million gallons per day. Let's not say 50, let's stick to 5. So I need 5 million gallons per day. Well, I don't know if this is an 8-hour operation, an 18-hour operation, or a 24-hour operation. So that's why your flow and volume are so important. You'll see we have MGD, so million gallons per day, million liters per day. And of course, I threw in some TDS to some of the common units of measures that are used in there, along with liters per minute. Now, we were just doing a trade mission in Brazil, and we noticed that not only do they use cubic meters per day, or metros cúbicos diarios, which there you go, it's a new word for me, they also do per hour. So the reason why I highlight this one out here is because we're no longer having to do the day, we're actually having to do the math around it. And interesting enough, it's easy to say, well, we're only operating for 5 hours a day, so now we know how much volume we have. Okay, and I threw in here parts per million and parts per billion. Of course, it's easy correlation between the two. 1 mgl or 1 milligram per liter equals 1 part per million. We won't be doing the math today. However, we have now added parts per trillion in there when we're testing for PFAS, which is another one of these contaminants that's coming up. We are testing it in parts per trillion instead. So that's PPT. It is pretty difficult to test for. You need labs that are certified to a very specific standard that can actually test for PPT, but it is out there, and it's when you're testing for dioxane and when you're testing for PFAS, and there's other some new ones that you're testing down to PPT. So important to know. No, how are we going here? How are we doing for time? Okay, I promised we were going to be going a little over here. So jumping on to metals, we'll keep this one short because we have done metals before. So iron and manganese, 2 metals not considered heavy metals technically. They do oxidize and precipitate. They oxidize and precipitate at different, let's call it different speeds, for lack of a better word, okay? So iron tends to oxidize a lot faster, so we find it in ferrous in nature, and then we are, of course, oxidizing and precipitating it to filter it out. Easy way of thinking about it is you've got a dissolved metal. In order to remove it, you turn it into a solid, you can remove the solid. Easy enough. Minerals, of course, are not that easy, and that's why we separate them in categories. Manganese is also found in suspended form. It's a lot slower to oxidize, and you typically co-precipitate it. So you co-oxidize your manganese with your ferric oxide. Oh, there you go. I didn't mean to read that, but there it is. Okay, so now I had to throw in the valence for iron just because you see it in there. I won't go into valences, but when you're oxidizing, you're basically changing the valence. That's the easiest form of it. Okay, so I added a little oxidation process because I think that's important. Process follows actually across the board to any metal. Again, there's some metals that oxidize at a faster rate than others, but this is the basic form of oxidation. So you start with your ferrous iron or your manganese or arsenic or uranium, and the list goes on. We oxidize it either by air or chemical oxidation or both. We're actually working on a project. We're bidding on a project with Megan. I don't know, Megan, if you're on today. It's been a busy week where we're oxidizing using both. We're doing both air oxidation and chemical oxidation. It speeds up the process, and we are primarily treating for manganese. And I even have a little table in there where you'll have a look at some of that case study. We turn it into a ferric oxide. Once we turn it into a ferric, again, you can precipitate it. It's a solid. It basically becomes into a solid. Now we can do mechanical filtration. And the same thing applies to manganese and other metals. So This is manganese. I did kind of peg it around pH just because it's a good segue as we go into pH. Iron and manganese all have different oxidation levels at a very different pH range, or slightly different pH range, but it's very important to focus on pH. I think pH often gets ignored whenever we go into the metal market. Simply, it's like, what can I throw at it to try to speed up the process to get it out? And I always fall down to pH, pH, pH. Everything focuses on pH, and along with arsenic. So you'll see the iron oxidation is normally a pH of over 6.8. Ideally, it's over 7.2. Manganese oxidation is a little higher, so at 7.5. If you have a pH of 6.8 or 7 with manganese, it doesn't matter what you throw at it. Doesn't matter what you throw at it. The oxidation and precipitation level is so that, it'll take, a few hundred gallons of water. So it's just not worth it. You've got to focus on on your pH. And oddly enough, with arsenic, specifically for adsorption, using something like titanium dioxide, we need to reduce our pH below 8.2. So it's kind of a fun game where you're chasing your goalposts to make sure that you're within that level. pH. So what is pH? I threw this in there. It was a kind of a fun little segue. 2 slides, I promise. Potential hydrogen. We measure acidity and alkalinity. There you have it, your whole gamma, right? You're going from battery acid with a pH of 0 all the way up to Drano with a pH of 14. I'm not really sure why they threw eggs in there. I don't know that I would have used eggs as an example to measure pH at 8. I'm pretty sure we could have found better examples, but there you go. You got, anything that you go into your system, tomato juice, banana milk, is always going to be a lower pH. Never mind soda. I am a big thing against soda. I will never touch it. And then when you go into toothpaste, of course, and you're going a little higher into your ammonia or even bleach, you've got to have much higher alkalinity. So easy enough. Now, I am going to throw this in because, again, it is another one of my little pet peeves when it comes into water chemistry. That is not how you write pH. That's not how you do it either. That isn't either. Okay, it's a potential of hydrogen. So it's important to understand what it is and to write it properly. And if I am no longer a teacher, I used to teach way back when, if I ever saw pH written like this, I don't care if your answer, your formula, or anything was right. The second you write pH wrong, it's wrong. That is the way you write pH. To a hydrogen, it's important to understand what it is, how it works, and how you write it. So now we're going to jump onto UV disinfection. Guys, I promised we were going to do 2 or 3 slides with every single subject we touched on. So thank you for bearing with me. So UV disinfection, UVT. So ultraviolet transmittance, okay? So this is tested specifically with 254 nanometers, which is a specific spectrum that we use for disinfection. Now, why do we use 254 nanometers? It is the best germicidal dose of light in order for it to disinfect. We won't go into spectrums today because, again, that's a whole other hour class. We can maybe leave that for next year. There you go. I love next year. Spectrums that are good, 186 nanometers are also used for organics or advanced oxidation. Today, for germicidal disinfection, we focus on 254. UVT, you'll see this in water reports. If you ever don't see it in a water report and you're dealing with surface water, it's very important to have it tested. If you can't get organics, at least get UVT. So you basically get a column of light. Yes, it's exactly a column of light. It's 1 centimeter by 1 centimeter. It looks like a little vial. You put it into a little device, and yes, that is a UVT spectrometer. You put in some light in there. That's as simple as it sounds, and you measure what comes out on the other side. Okay, so UVT of 0 is exactly that, 0. There is no light penetrating through that 1 centimeter column of water. As your UVT goes up, it basically means you have better water. Now, interesting fact, you can get a vial of water that will be clear, and your water will be clear. But if you have anything like sugar, again, an organic, and you dissolve it inside the water, it's considered an organic, obviously. So water will not penetrate through that, and the water will be clear, and this applies to other organics, obviously, obvious disintegration. But you can try to flash any kind of, put some light through it, you will not read it on the other end, which is why testing for UVT, regardless of what your color of the water color looks like, is important. Especially, of course, when you're treating with UV disinfection. So pathogen inactivation chart, we did do a whole nother series on pathogens and UV disinfection. Pathogens are divided into 3 groups. You've got your bacteria, your viruses, and your protozoas. And here's your inactivation. I threw a little note in there of the millijoule per centimeter squared to microwatt per centimeter squared, just so it's easy to do math. I always remember it as 1 kilometer equals 1,000 meters. It's easy. You divide it by 1,000. So the chart is in millijoules per centimeter square. Kind of rolls off your tongue a little bit. So you'll notice, even E. coli, your inactivation is very low. Like you're looking at 6.4 and 7.9. Very, very low, 10 or 16. 3 log inactivation versus 4 log inactivation. It's easy to remember how many digits is there. So 3 digits is 99.9, 4 digits is 99.99% inactivation. And I know, Andrew, you're going to call me out on this because we've had this discussion a few times. In California, when you do water reuse, so you say you're using rainwater or storm water and you're reusing it, they ask for 6 log reduction. So now we're looking at 99.999. Did I get that right? Yes, I did. So 6 digits. I know. That's California for you. So as you can see, the inactivation rate to this, other than your rotavirus, is pretty good, pretty acceptable parameters. Again, if you want to convert it into microwatts, you just add 1,000. So 7,000, 7,000. So dose additivity. Dose additivity is something that's very important to understand. And yes, there's a lot of graphs and charts that show you how dose additivity works. We will not get into that today. But if you do some simple math, it's pretty easy. Dose additivity dictates that as you reduce your flow and you improve your UVT, you can maximize your disinfection level. So NSF standard says that you need to have a minimum of 50,000 microwatts per centimeter square at 75 UVT. So that's a specific level. You test at 75 UVT, you need to have a minimum of 40,000 microwatts per centimeter square. Now here's a catch. This is at the end of lamp life. So some lamps last a year, some of them last 2 years, which is 18,000 hours. Don't ask me why, I know. So if your lamp is rated for 18,000 hours, at the very end of your lamp life, you're going to see depends on the lamp that you're using, a high output lamp, low output lamp, amalgam lamp, you need to hit that dose. Now, I'm going to use my mouse here for a little bit because I love charts. As we improve our UVT, we improve our disinfection, our dose. Okay, so 75% UVT, we're hitting 40,000 microwatts. As we improve our UVT, look at it just going up to 90% or 95%. We're now at 70,000 microwatts, so very, very good, or 70 millijoules, easy. Okay, as we reduce our flow, so we get a unit that's rated at 500 gallons per minute at 40,000 microwatts. We reduce our flow in half to 250 gallons per minute, and we have moderate 85% UVT. Now we're hitting it at 115,000 microwatts. So here we saw that you can inactivate something like crypto at 4 log at, let's say, 8 milliliters per centimeter square. Here we are potentially hitting it with 100. Which one did we look at? This one, 150. So way beyond any set parameter that they're looking for. And never mind if you restrict a 500 gallons per minute down to 50 gallons a minute, that's a little extreme. We're going into 1.1 million microwatts per centimeter square. For those that don't remember the previous slide, I added in here as well. The 1 millijoule equals 1,000 microwatts. Depends which one works. One of them just kind of goes a little faster, just kind of rolls off your tongue a little. So UV gravity filters. You see that was short. I kept it short on the UV. So gravity filters. This is, of course, our standard dissolved flotation. This is what I say at AWC, our bread and butter. We've been doing this for many years. We have, I would say, a good percentage of our plants we focus on DAFs. And we do standard DAFs, like a train like this. We also have retrofitted DAFs, which we're working on for a few projects, including the one in New York, which Troy will be presenting on, yes, next year, on retrofitting DAFs. So you can do these. We are primarily focusing on organics and turbidity whenever we use DAFs. There is some chemical addition to that in order to achieve the polymers and the flocculation that you need on this. But you'll notice that we don't typically use DAF if we're looking at metals, not that they won't reduce metals, but we would use a standard DAF for organics and turbidity. Now we jump on to our direct filters. The nice thing with direct filters is you can use any media you want, right? So we can use sand, anthracite, carbon, zeolite, manganese dioxide if you're treating for metals. Now, this train looks a little small. It was more for the rendering. Okay, so you can make it as long as you want. We're doing with something like this, you can go up to 1,500 gallons per minute per train. So we added it in liters per second, so 95 liters per second. So some pretty decent flow rates per train. Now, we did, of course, you've got your trade-off. You've got decent amount of organics, okay, for really good for metals, but when it comes to NTU, it's got its limitation to how much turbidity you really want to be pushing through it. So 10 to 20 NTUs. This is one that we were just working on with Megan. Actually, it's not too far away from here. We were treating for manganese. I kind of threw it in there as a case study because we're using now one in Alberta too. I don't know if you were able to make it there, but Carla is from Edmonton. We're working on this one. So we're doing 2.5 MGDs, 2.5 million gallons per day, or 9.5 liters per million liters per day. We're doing 1,700 gallons per minute. There you go, easy. That's the difference between volume and flow. Easy enough, important to have both metrics. Water quality, we're treating for 1 part per million iron. Manganese is what we are focusing on, but of course we co-precipitate our iron. We already covered that. Our pH is good. We don't have to do much with the pH. pH of 8 is actually perfect for manganese. And we have some relatively low turbidity. These are peak numbers, mind you. There's always a RAID, there's always your average, but I try to be on the conservative side. If you tell me your peak is 5 gallons, 5 NTUs of turbidity, I really do need to design it around that peak. As you can see, 2 trains, easy enough. If they ever want to expand to which they will consider in the future, eventually bump it up to 2,400 gallons per minute. So pretty straightforward. Now, tube settler, this is all under the gravity filter gamma. With tube settlers, also known as lamella filters, Ryan Harvey had a really good presentation last month where we covered this. I kind of broke it down with some subtitles. I'm not going to read them through them all. We kind of went over here, but we had our flash mixing. We have our flocculation as part of our process. Then we go into the clarification going through the tubes, and then we follow it up with filtration. We have a couple people here that logged in from Brazil. I don't know if you're there. Como va você? Particular is you can go up to 1,000, potentially up to 2,000 NTUs, as long as it's optimized properly and you do the proper chemistry in order to treat for high turbidity. In their case, they're drawing from a river. We can do this. We've also done a few of these in Arizona, and if you were part of the presentation that we did on ST plants, you'll notice that we did a few case studies. So on those, we kind of covered those. So last but not least, we did go over emerging contaminant month. I was corrected and say rather than calling it emerging contaminants, because the contaminants are already there, we should call it contaminants of emerging concern. Did I get that right? Yes. Contaminants of emerging concern. The ones we covered are PFAS, microplastics, 1,4-dioxane, and cyanobacteria. We didn't cover how to treat them. We were going to do a follow-up on that one. We went what are they and how they're caused and some of the toxicity levels for each of them. We are having a follow-up presentation primarily on PFAS and on cyanobacteria on how to treat it and some of the technologies. Again, it's a lot of information to put into 20 minutes. So those are some of the recordings. If you've missed one, we have the cyanobacteria, we have the dioxanes and the microplastics. The microplastics did really good. We actually had a lot of really good reviews on that. So if you missed any of them, you can always take a look at it. I will put a little note in there, and I apologize for the shameful plug. I'll put a little note in there so that you can kind of follow it and catch up. So here we go. We're wrapping up. It is now 10:27. Okay. Finishing it up here, I promise. So 2021, what do we have in store? Yes, let's hope we get over 2020. Man, I'm so ready to turn a new page and start this new year from scratch. So here's some of the things that we're going to be doing in January or February, so stay tuned. We're doing PFAS treatment. Again, like I mentioned, we're not going to be doing what they are. We've already done that. We're going to be covering how to treat them. So ion exchange, granular activation, carbon for adsorption, and electrochemical advanced oxidation process. That's quite the mouthful. So these are some of the technologies we're going to be covering. How to treat for cyanobacteria and cyanotoxins. It's kind of the chicken or the egg. Which one do you go for? Do you go for the bacteria or do you go for the toxins, right? So we're going to be covering both of those in some of the technology. We'll also be doing desalination brine management. We had talked about this before because we did get a little mentions about how desalination is increasing brine in the oceans and what it's doing to the environment. So I thought we could sneak in there a little desalination brine management, kind of cover how you're managing it. That is not my field, so we have somebody that's going to be coming in and going over that. It's actually pretty interesting. I'm looking forward to that one. DAF retrofits. We're going to do a couple case studies on DAF retrofits. Troy volunteered to help me out with this one, what we can do with DAF and some of the, again, case studies we've done in the past. It's actually not that hard to do, believe it or not, as long as you're doing it right. And of course, measurements, you got to, sometimes you measure, you don't measure once or twice, you measure 3 times to make sure you get it all right. And then lastly, we're going to do MBRs. Our chief engineer, Ruth Ruxford, is going to be doing a presentation on our webinar on our membrane bioreactor. Stay tuned for that one. We're going to go a little further in depth than this is the box with membranes. We're actually going to go through the process of how they work, what is their applications, and when you're going to be using it for very particular cases. Allison, thank you for joining. I see your name. It's right on the A, so it's kind of standing out right there. This is exactly what we're going, and I know I owe you an email on this. So there's your membrane bioreactors we're going to be covering. So that is, oh, there we go. I forgot one more, ion exchange. So yes, we're going to be going into cation versus anion. For those that are not familiar with ion exchange, a negatively charged ion with its corresponding resin versus a positively charged ion with its corresponding resin, and then selective resins are in there too. So we are going to have a guest that's going to come in. I have a really long list of questions, so stay tuned for that one. That one will be fun. So that's what we're going to be doing in 2021. I'm going to open it up for any questions. I know that we kind of went over our time, but I did warn you. No, it looks like we already have a question coming in. Give me a second. Sometimes this is a little slow. So don't be shy. Turn on your camera. This is the last one of the year. Please ask us any questions you have, and I'll take anything. So go for it. Okay, so I have a question here, and I'm not trying to ask myself, but a question did come in via email, and it was primarily on the oxidation. Why are we oxidizing? When you oxidize metals, it is really the easiest form of treatment when it comes to metals. You really want to make sure that you're doing a right job in getting the dissolved metal into a solid. It's really the way that you're removing it. Not that we can't do it with, obviously we can't do it with minerals because minerals do not oxidize, and that's why we can only focus on metals. When we go to minerals, which we'll cover with ion exchange with minerals, specifically minerals, we are either using reverse osmosis or some form of mechanical treatment, although I wouldn't call reverse osmosis technically mechanical filtration. That's my bad. And then, of course, ion exchange to remove minerals. Unfortunately, when it comes to minerals, those are the two that we're really going to be focusing on. You cannot oxidize them. You can't precipitate them. You can't coagulate them. Minerals are minerals. That's how we remove them. So a quick shout out to my dad. He was able to log in. Hi, Dad. Thank you for logging in for our last one. Oh, and my uncle Scott also from California.
Our pleasure.
There you go. My uncle Scott is also tuning in from San Francisco, so thank you for joining us. So that's a wrap. I want to ask everybody to stay safe and healthy, and I will see you in 2021. Again, if you have any questions, you can always shoot us an email. We're always here to help. So thank you very much and goodbye. Thank you for tuning in.